I don't know what kind of passcode it wants. Is there a code that you want or that you have there for that Zoom meeting?
Well, this has never required it before, but meeting. Usually I just hit invite.
Normally, like, we were just supposed to retry that, if not restart the app. But I guess we could do that too.
Good morning, everybody. Got crack tech people on this. And other people too.
I can go up and call the office too. They'd know.
Maybe I'll just call. Should I call tech and ask him? Hey, Corinne, are you here? I invited her, but she just won't be able to see the chalkboard. Maybe I can. She's probably not. She's probably just looking for the recording once it's been recorded.
Probably.
And so what I'll probably do is just do that. Fight again.
Rotate. One thing you could do too is make sure it's not on this computer. That could be the issue because normally it's the computer just trying to.
Yeah.
Okay. Well, I can always talk to her another time and fill her in. So I'm not going to take the whole class period trying to figure out this. So. All right. You guys can spend another couple minutes working on it, but don't knock yourselves out. Okay. We have been looking at the work of Benjamin Franklin and his work with the forces, between charged objects, the electrostatic forces. But he was lamenting that he didn't have any numerical kinds of laws, right? So his was very qualitative in his approach. We get to Coulomb, Charles Coulomb, the French scientist, who basically does the first quantitative measurement of forces between electrically charged objects.
Did you sign into Zoom?
And he's famous for using He's famous for using what's now known as a Coulomb balance. I think he called it a torsion balance.
There we go.
Twisted balance. Okay, thank you. Beautiful. Thanks, guys. And so what he does is he's basically, if you watch the lecture, you read the text, you know what he's doing. He's basically charging up these spheres, and what happens is when you charge them, one of them is suspended from like a wooden rod or kind of I guess it's some kind of insulating rod, and there's a vertical wire, and when they're charged, they repel one another, and this wire twists. And by measuring the twist of the wire, or alternatively how much you have to twist the wire to bring it back toward the other ball, that can provide you with a quantitative measurement of the force between charged objects. Okay? So that's what we're going to be doing in lab today and tomorrow, is using a torsion balance that's very similar to that of Coulomb. It's not going to be exactly the same, and in some ways I think it's better, but in some ways I think it's worse than Coulomb. Okay? So what we're going to be doing that measurement. But the upshot of his measurements was he was able to find a relationship between force and distance between two charged objects. If you read the text, he basically doesn't give what's now known as Coulomb's law in its mathematical form, in its full beauty, okay? But he does tell you how the force depends on distance. So I'll remind you what Coulomb's law is that the force between two charged objects is equal to some constant, which is now called the Coulomb constant. Think about it as a constant of nature, like the charge of an electron or the speed of light or the mass of a proton. Coulomb constant times the product of the two charges divided by the distance between them squared. That is Coulomb's law. So this is the force of either attraction, if they are oppositely charged objects, or repulsion between them. This is Coulomb's constant. And frankly, I never remember what Coulomb's constant is, K, but I do remember that K is sometimes written like this, K equals 1 over 4 pi epsilon naught. That's a Greek letter epsilon with a little 0, epsilon naught. And I happen to remember what epsilon naught is, so I can always remember K in that way. So what is epsilon naught? It's called the permittivity of free space. It's kind of a property of the medium of space itself. And you might think, well, that's weird. Space is like nothing, so how can it have properties? Okay, yeah, that's weird, right? It's going to be, we're going to come back to this later on, but space itself seems to have certain properties, okay? And it's going to show up, epsilon naught is going to show up later on when we're talking about the speed of light. It's related to the speed with which light travels through space, okay? Here, it's not at all obvious that it has to do with the speed of light. Here, it just shows up as some way that the force is related between charged objects, okay? The value, by the way, is 8.854 times 10 to the minus 12th. And what are the units of that? Well, I forget the units, but we can figure it out. Anytime you have a formula that includes some variable or some constant, you can figure out the units by rearranging the formula, right? So if I solve for K in terms of force and charge and distance, I can figure out the units of K have to be, okay? So the units of K, I'll put a square bracket around it. That means the units of K have to be the same as the units of force times the units of R squared, the distance squared, divided by the units of charge squared, right? That's kind of just a unit formula. It tells you what the units are. And we know that force is measured in newtons, distance in the international system. You can use whatever units you want, but if we use the international system, newtons, meters squared, and coulombs squared. So that's those are the units of K, and of course then the units of epsilon are going to be the inverse of that, because 4 pi doesn't have units. So the units of epsilon naught would have to be coulombs squared over Newton meters squared. And like I said, my memory's not great, I forget these things, but the nice thing is that all you need to do is remember a formula that has it in it, and you can immediately find out what the units are. Does that make sense? I think that's a useful trick to use. All right, anyhow, this is Coulomb's law, by the way. These are the charges of the objects, and this is the distance between them. Okay? Questions about that so far? So all I'm telling you is what Coulomb's law is. He arrived, basically he said that the force is proportional to 1 over the distance squared. That's kind of how Coulomb described it. But you can see that here. But this also shows its dependence on the charges, and exactly, it's an equation, not just a proportionality. Okay? Good? All right, so if you're uncomfortable with what we mean by an inverse square law, what this is saying, let me make a plot here of the force versus the distance. Let's suppose that you were to place 2 charged objects, 2 positively charged objects, at some distance capital R from one another. That's the center of one to the center of the other. And they're at some distance capital R from each other. And you measure the force to be some value. Okay, we'll call this F naught. Okay, and you get that data point. What happens if you were to double the distance? That is, go to 2R, twice the distance. What would happen to the force based on that formula? Would the force go up or down, first of all? It would go down, right? The farther apart the force is lower. How much lower? Yeah. A quarter as big, exactly. 1/4 as big. So if I break this up, so it'd be F naught over 4. So the next data point would be there, if in fact that formula is right. Okay? That's what we mean by an inverse square law. If you go, you can figure out the force for plugging in a capital R, and then you can figure out the force for plugging in 2R there, and you'll find that the force is 1/4 as big. Okay? And then what about if you went to 3R? What would happen there? The force would be weaker again, but how would I express the force? Pardon? 1/9 of the original. So 1/4, I don't know, it'd be something like this, like F naught, my scale is too small, F naught over 9. So it's like that. So it's kind of a law that looks like that. Okay, that's what he is claiming. All right? Questions about Coulomb's law? Okay. What I want to do during this period, I mean, we could talk more about the details of how he carries out experiments and how, kind of the apparatus works, some of the nuances of it. But I want to make sure that we get to the homework problem, because I think the homework problem is a really nice opportunity to learn how to apply Coulomb's law and a refresher on how to use vectorially add forces. Okay, so I'm going to step through this homework problem, make sure we understand how to approach this. Okay. All right, so the homework problem that you have this week, if I remember it correctly, you're told, well, so you guys have two homework problems, 6.2, and I think I have a typo on my website that said 6.4 originally, I meant 6.3. So 6.2 and 6.3 are the two problems you all supposed to be working on this week. And 6.2, what you're doing is you are told that you have three charges and they are on the vertices of an equilateral triangle. So you've got charge 1 right here, charge 2 right here, and charge 3 right here. I don't remember what I labeled them. Let's call this one charge 1, charge 2, and charge 3. How's that? They're on the vertices of this equilateral triangle. And you're told what their values are. So this one, can you remind me, what is charge 1 is how big? Someone have that info handy? Yeah. 1 nanocoulomb. Okay, so I don't want to work with nanocoulomb. Let's just say +1. Okay, we'll call it +1, and you can insert nanocoulombs if you want. I don't want to carry around 10 to the minus 9 on the board. Okay, and charge 2 is what? 2 nanocoulombs. So I'll call that +2. They're positive, right? Yeah. Okay, and charge 3 is what?
2.
+2. Okay, so we have 2 + 2 nanocoulomb charges and 1 + 1 nanocoulomb charge, right? And what you're being asked in this problem is to find the force acting on each of these three charges. Okay? Now, I always, so that's the goal, is to find the force, and I would specify that we want the net force or the total force on each of the three charges. Right? And are you told anything else here? Are you told the distance between them? 1 millimeter? Okay, so there, and it's an equilateral triangle, so that's D, and that's D, and that's D, and it's 1 millimeter. I'll just call it 1 for now. Okay? We can plug in units later if we want. Okay? Now, when we do a problem like this, it's very tempting to immediately start grabbing formulas and plugging numbers into formulas. Okay? Before you do that, I always think it's very useful to try to guess what's going to happen before you do any math. Try to think about it in an intuitive way, kind of large-scale way before you use any formulas, because it will actually guide what formulas you're going to use and how you use them. Okay? And it might be much simpler than you realize. So let's try to say everything we can about this problem without using any formulas or numbers. Okay? I strongly encourage you to do this whenever you're doing a physics problem. So let's think about this charge up here, charge 1. Do you want to guess which way the force is going to be acting on it? First of all, how many forces are acting on it? 2? Why do you say 2?
Actually, no. I understand the answer. It's a net 1 force because the 2 charges are the same.
Okay, so there's a total. There's 1 force in total.
Yes.
But how many individual forces? Maybe I'll ask it this way: how many individual forces are acting on it? Do you have to kind of add together?
2.
2, right? What are those forces? Well, this guy right here is pushing on him. I'll use him, sorry, okay? And this guy right here is pushing on him too, right? So those are the Coulomb repulsion acts between every 2 charged objects. So he's pushing on him and he's pushing on him. Which way is this one pushing? If you were to kind of draw an arrow, a vector representing the direction of that guy pushing on him, which way would I draw, roughly speaking? And up and to the right, right? Because it's a repulsion, it's going to be along a straight line connecting those two. And it's either going to be pushing away if they're both the same charge or pulling toward if they're opposite charges. So there's going to be some force kind of pushing up that way due to this one. What about this one? That one's pushing also, right? Which way is that force going to be? Yeah. Go ahead. Yeah, exactly. Up and to the left, that way. Good, so you got these two forces, but when I'm asking for the net force or the sum or the total force, which way is that going to be pointing? Like overall, there's a force pushing that way, a force pushing that way. What do you think is going to happen overall? Yeah, what do you think?
Somewhere in the middle.
Somewhere in the middle, like so.
Those two forces, yeah.
Okay, so
Like a straight line up.
straight up. Why do you think that? You're right, but why?
Just because the other forces are pushing, so they kind of will equal each other out almost.
Bingo. There's like a symmetry here, right? Like the whole thing is symmetric. So picking out a symmetry in the problem is a wonderful way to simplify the problem. This one's going to be pushing up that way. This one's pushing up that way, but everything's symmetric. So kind of the horizontal parts of the pushes are going to balance each other out. And all you're going to have left is a straight upward push, right? Does that make sense? So it's good to kind of keep that in mind because it's going to, you know, life is hard enough. We don't have to add up things we don't need to, right? So keep that in mind. So we're going to have a kind of straight upward force. So if in the end we find a force that's like pushing straight sideways after plugging into our math equations, chances are we're probably wrong. Okay. All right. What about this one right here? How many forces are pushing on charge 2? Sure. Okay.
Should be 2 again.
2, right. This one is pushing him which way?
Down to the left.
Yeah, along that way. And this one's pushing on him straight left. Okay. There's going to be kind of 2 forces pushing that one. What do you think the net force is going to be? You know, here it was kind of pushing straight up like this, the net one. Is this one going to be kind of pushing straight, I guess, perpendicular to this face like that? What do you think? Yeah, what do you think, Gavin?
I think no, because the charge is greater than the charge.
Exactly. There's not the same kind of symmetry here, right? So if you kind of think about this half and this half, you got a +1 charge here, but a +2 charge there. So this force pushing it that way is actually stronger than the force pushing it downward. So you're going to have a net force that's a little bit more kind of at a funny angle, like a little bit more upward and to the left. Does that make sense? Okay. What about this? Once we've calculated that one and that one, do we need to calculate that one? Why not?
It's just the opposite of the problem.
Yeah, remember this whole problem is symmetric about this. So once we figure out the size of that force and the angle, that's going to be the exact opposite. So you don't need to go through all the calculations again. Once you figured out the left side, you can just mirror it to the right side. Does that make sense? Okay, so this is really good to think about a problem like this before you do any math. I know the tendency is to grab a formula, start plugging in. Don't do that, okay? Think about everything you can without doing math. All right, so now let's do some math. Let's first consider charge 1, all right? So charge 1, if I write here, can you see, Michaela, if I'm writing on this board?
Yeah.
Or would you prefer I come back over here and erase it?
Either one is fine.
It's easier for me to write over here. I'll erase this stuff. All right, so I'm gonna draw this charge kind of all by itself. And what I'm going to do is I'm gonna commit to a coordinate system that's gonna help me express these forces which act as vectors in different directions, okay? So I'm gonna call this right here the x-axis, and this right here the y-axis, okay? And I'm thinking about this charge right here. So let's draw vector diagrams of each of the forces that are acting on this charge. Well, the one down here is going to be pushing him up in this direction. So maybe we'll call that force 2, because that's from charge 2 pushing on that charge. Call that F2. And then we've got another force that's pushing up like this, and maybe we'll call that F3. Okay, and these are little vectors. They're a force represented by a vector. We talked about vectors a couple of weeks ago, okay? So these have a magnitude, a size, and a direction, all right? Now, how do we figure out the net result of those 2 forces pushing on it? Well, here's what we're going to do. We're going to think about each of these vectors as the sum of two other vectors. In other words, we're going to decompose each of these into its components. So this vector right here, this force, can be understood as consisting of a sideways force. I'll call this F2x, that sideways force, and a vertical force like this, F2y. So it's a horizontal force and a vertical force added together gives you this total force right here. Does that make sense? And this is a 90-degree angle there. And likewise, I can project this one down here and say this one, we can write this as F3x, and this is F3 in the y direction. And once I've done that, you can probably see that F2x and F3x, what do we know about those two vectors, or those two forces that are represented by vectors? What can we say about those? They're equal in size, right? Because they're both pointing at the same angle upward like this. So when you project both of those down, they're going to have the same size, and so those are going to be balancing each other out. That's exactly what we kind of thought was going to happen. The sideways forces balance. Notice that they both have an upward force, though. Those are going to add to each other. Those complement each other. They help each other. Okay? So to figure out the total force on this guy, all we need to do is calculate the magnitude or the strength of that force and the strength of that force and add those two together to get the total upward force on this charge. Does that make sense? All right, so we have to find the vertical component of each of those two vectors. So we need to find what is F3y? How strong is that? What's the magnitude? So what is the magnitude or the size of this force vector? Okay. To find that out, what do we need to know? Sure. So you need to find how big that force is, right? What else do you need to know? Do you need to know anything else? What? Yeah, you'll need to, if you know the hypotenuse of that triangle, to find a side of it, you're going to need to know some angle in there, right? I mean, we know the 90-degree. That's not enough. You need to know the angles of that triangle. Do we know the angles of that triangle? If I draw it up here, so this is kind of aiming up in this direction. We know this angle right here, theta is 60 degrees, right? And we know this one is the same angle, theta. And if we draw a horizontal line right here, notice that this angle is the same as this angle. Why is that? Because you have two parallel lines, and then you have another line transecting them both. And so the interior angles right there are going to be the same. Right? So you have to like dig back into your geometry knowledge. Okay? So that angle theta is going to be the same as this angle right there, which is this angle right here, theta. Does that make sense? So once we know this, and we know the angle, then we can probably figure out F3y, vertical part, right? What's the relationship between the hypotenuse, this angle, and that side? How do we figure that out? Any non-Michael person want to say something? I'm smiling behind my mask, by the way. Yeah, what do you think?
Fx and Fy are the same, and then
The x component and the y component are the same?
length, and then the hypotenuse is the same. Square root of.
So it sounds like you want.
Square root of 2 to 1 to 1 ratio.
So it sounds like you are trying to use like you're assuming this is a 45, 45, 90 triangle.
Oh yeah.
Right? So if this was a 45, 45, 90 triangle, they would be the same side. It's not a 45, 45, 90 triangle. It's a 30, 60, 90. I know it looks 40, I didn't draw it quite right. It's actually a 30, 60, 90 triangle. So you can't quite do that. What do you think, Evan?
Is it sin of theta equals F3y over the hypotenuse?
Is that what you're saying? Sine of theta is F3y over F3, right? Because sine of theta is opposite over hypotenuse, so you're exactly right. So you got to remember your SOHCAHTOA stuff, right? Then you can just rearrange that to get that F3y times sine of theta, right? So F3y, the size of that is going to be whatever the hypotenuse is times the sine of the angle theta. Excuse me. Are we good so far? Okay. Now, we know what theta is, so we can figure out sine of theta, right? For a 30, 60, 90 triangle, anybody remember? You have a 60, 30, 90 triangle, what the relationship between the sides is? I know you said 1, 1, root 2 for a 45, 45. What about 30, 60, 90?
1 root 3, 2.
1, root 3, 2. Exactly. 1, 2, root 3. 1, root 3, 3. Exactly. So if you have sine of 60 degrees, it's going to be what? Sine of 60 is ratio root 3 over 2, right? Opposite over hypotenuse, right? See how I did that? So you should know stuff like this. I'm not going to give you some funny angles that you have to like do on a test or something, because you can't use calculators on tests. So I'm going to give you triangles that you should know the sides to. Okay? Like 45, 45, 90, 30, 60, 90. Okay? So then you can just plug in the root 3 over 2 for this. But now we need to find the hypotenuse F3. Do we have enough information to find that out? The strength of the repulsion force overall between those two charges. What do we need to invoke in order to determine that force? Sure.
We have to do like some vector addition to, since there's a charge pushing back on, so like Q1 is pushing back on Q3 with that.
So that is true that 1 is pushing back on 3, but if 1's pushing on 3, that is not a force acting on this guy. Okay, so you can ignore every other force in between other things in this triangle. All we care about right now is the forces acting on this one. There are 2 forces acting on this one. We're trying to figure out what the strength of that one force is so far. Okay. How do we figure out the force of repulsion between 2 charged objects? Sure.
Coulomb's law.
Bingo, Coulomb's law, which is K times the charge 1 times the charge 2 over the distance between them squared, and then we'll multiply that by root 3 over 2, right? Do we know what charge 1 is? Or whatever the first charge is. The 2 charges we're interested in is this one and this one, right? Do we know what the values of those charges are? Yes, +1 and +2 nanocoulombs. So we see F3y is going to be K. I'm not going to plug in all the numbers. So let me just write down K. You can plug in, epsilon naught, figure out K and plug in K, right? And then the product of the 2 charges, well, you got a +1 charge and a +2 charge right here. They're in nanocoulombs, I know, so you'd have to multiply times 10 to the -9 for each of those. I'm not going to write that up here. And the distance between them is 1 millimeter, so I'm just going to put 1 millimeter in there like that. And you'd have to write it in millimeters, I know, but you can do that, okay? And then multiply by root 3 over 2, and that will be the strength of this force right there. Does that make sense? I'm sorry, that's the strength of the vertical component of that force. So now, what is the net force? Is the net force on charge 1? Anybody want to field that question? Yes?
Is it just 2 times the vertical force?
Bingo. Exactly. Why go through all of our work again to figure out for that one? We already know it by symmetry. So the total force on charge 1, we'll call that force on charge 1, is going to be K times 1 times 2 would be 2, well, let me see, 2 over 1 times root 3 over 2, but twice that, right? Then you cancel out your 2's and you solve it. Okay, does that make sense? Do you see how we did that? So this is a nice problem where you can, you have to remember basically 2 things, Coulomb's law and how to do trigonometry, okay, in order to solve this problem. That doesn't mean, I'm not trying to imply it's an easy problem. You got to like be careful and like, what don't I know, what do I know, kind of draw the pictures carefully and work through the steps carefully. But it's not like, it's not a really complicated problem. It's only complicated in the sense that you have to do steps in the right order and think about what do I need and figure out a way to get there. And that's not always easy, okay? Are we happy with this so far? So you can cancel out these 2's if you wanted to, plug in your K, and you've got the force acting on charge. Good? Let's talk about this charge down here now. So what is the force on charge 2? I need to erase this stuff if you don't mind again. Is that all right? Okay, so let's once again draw that little charge. This is charge 2. And let's again draw some axes like this. And let's draw the 2 forces that are acting on this guy. So which way do I want to draw vectors representing forces? Down and to the left, kind of right, kind of like that, right? Force like this. And let's call that F1 because it's the force that is exerted by charge 1 on charge 2. And what else? Directly to the left, correct? So we'll call that F3. As I'm drawing this, let me ask you this question. Do I want to make, if the length of that vector is indicative of the strength of that force, do I want to make that vector longer or shorter or the same size as the other vector?
Longer.
Why longer?
Because it's the magnitude of the vector.
Right, it's the magnitude. How do you know the magnitude of the leftward force is bigger than the magnitude of the downward force? So you're right, but why?
Because charge 1 only has value of 1, charge 2 has a charge 3 has value of 2.
Exactly. And remember that the magnitude of the size of this force depends on the product of the 2 charges. So the product of 2 and 2 is going to be 4. Product of 2 and 1 is going to be 2. So this one's actually going to be twice as strong as that one, right? Good. Okay, that's good to just kind of keep in mind. Now, what do we do? Well, let's call this the x-axis and the y-axis. So let's figure out the components of these vectors. So first of all, F1, once again, that one we can kind of break into a downward or an F1y, is a downward force, and also a horizontal or leftward F1x force, right? See what I did there once again? Decomposing it. What about F3? What are the components of that one? It's just an X. That makes our life easy, right? So we could have like made this coordinate system in some funny direction so that they both had X and Y coordinates. Why would we do that? Let's pick the orientation of our coordinate system so that one of them lies right along it, so it's actually easy to compute, right? All right, so whatever we find then, the total or net force is going to have a leftward component that is the sum of that one and this. And the downward component of it is going to be just due to force 1, right? So the total, I'll call it F net in the X direction is going to just be equal to the strength F3 plus F1x. It's going to be kind of the sum of that one and that one, right? Whereas the net force in the Y direction is going to be just whatever the strength of F1y is. You see that? All right, so now we've got a work cut out for us. Let's figure out, let's do the easy one first. What's F3? What is the strength of F3? Well, just use Coulomb's law again. K times, what are the charges involved? It's these 2 charges, right? So you have +2 times +2, and the distance between them is 1. And once again, I know this is millimeters and nanocoulombs and whatnot, but I'm not going to write all that up here right now. And there we have it. Oh, by the way, it's squared, but 1 squared. I guess I could have put a squared here also, but 1 squared is 1, so I didn't really need to put a squared. Okay. I guess if you would 0.001, because it's 1 millimeter, then you do need to square it and be more careful. Okay. All right. Everyone happy with that? All right. What is F1x now? What's that component right there? We got to figure out some angles in here then, right? So let's call, so which of these angles, like out here or in there, which of them is going to be a 60-degree angle? The outside angle, right here? This one? Right? Because if you think about, yeah, horizontal line like this and one down like this, that angle is the same as that one, so, right, exactly. So this angle is 60 and that angle is 60, right? And if that one's 60, then is this one in here going to be 60 or not? Not, right? That's going to be that's going to be 30, so I have to add 90. So this one down there is going to be your 60-degree angle, right? So those angles are going to be the same. See that? Got to remember a little bit of how to do geometry here. And now, how do we figure out what this side of this triangle is? One. One. Do you mean that's strength of the?
That's short.
Oh, okay. So so if this is 60, the ratio of this side. Okay, so when you say 1, you're really talking about the ratio of that. If we call that 1, then that would be 2, and that would be √3. Okay. So I mean that's okay, but we're gonna have to put in a number for that. So that one isn't necessarily going to be 1. It's going to, whatever this is, that's going to be half of that, right? So, does that make sense to you? So maybe a better way to do it, is it going to be sine theta or cosine theta or tangent theta? What trigonometric function is going to relate the hypotenuse to the bottom?
Cosine theta.
Right, so cosine theta, just remember cosine theta is going to be adjacent over hypotenuse, right? So cosine of this angle is going to be that side divided by that side, right? And as she mentioned, cosine of 60 degrees is going to be 1/2, right? So to figure out F1x, basically we're going to take the hypotenuse, which is F1, and multiply it by cosine of 60, or multiply it by 1/2, which I think is what you were suggesting before. See how I did that? Okay, so now we've got to figure out what F1 is, the hypotenuse. How do we figure out what F1 is? That's the repulsion force. What do we use? Coulomb's law, right? Which is going to be K times, what are the two charges involved here? This guy and which one? We're doing this downward force like that, which involves the product of which two charges? Yep. Yeah, these two right here. Exactly. So you have a +1 and a +2. It doesn't matter what order you put them in because multiplication commutes, right? And then the distance between them, 1 squared. And then you have to plug this in right there. So you take a half of that, and that will give you F1x. Right? So F1x, if we wanted to write that out, F1x would be 1/2 of K times 2/1 squared, right? So that's going to be this component right here. And we still have to find F1y, right? And what would F1y be? It would just be F1 times what? with this vertical part right here, how is that related to the angle 60? What?
1/√3.
Okay, 1/, so exactly, it's 1/√3 times the hypotenuse, because the sine of theta is opposite of hypotenuse, right? Which would be a ratio, not 1/3, but √3/2,
Oh, right.
right? So maybe we'll do this a little more slowly. F1y would be the hypotenuse times sine of 60 degrees. Because sine of 60 degrees is opposite of hypotenuse. So opposite is sine of 60 times hypotenuse. Okay? And we know sine of 60 is going to be √3/2. Okay? So that'll allow you to find F1y. Okay? Yes, good. All right, so then we'll know F1y, which gives us the vertical part of the force. We'll know F1x and F3. So we've got F1x and F3. You have to add those two together. So then we'll have the overall net force in the x direction and the net force in the y direction. Right, so I'm kind of sketching this out without plugging in all the numbers at this point. Good. Now, what we can do now is, let's suppose we wanted to find this total force. Like if I were to draw like a parallelogram here, which is basically this net force is going to be represented by the diagonal of that parallelogram. You might be able to see that because the horizontal part of this is going to be the sum of this and that, which is up here also. So this right here can also be seen to be F1x. So that and that give you the horizontal part of the entire force, and this one down here gives you the vertical part. So overall, this force is going to be like this. This is going to be the net force on it. How do we figure out what the net force is now? We have the vertical part and the horizontal part. How do we figure out what the net force is? Yeah. You can use the Pythagorean theorem, exactly. So we can just say that the net force on charge 2 is going to be the square root of the sum of the squares of the two components. And what are the squares of the two components? Well, the x component is F3 plus F1x, and the y component is F1y. So you kind of plug that number in, square it, plug that number in, square it, take the square root, and then you get the net force on that charge. Make sense? Okay, we went through the second one a little bit more quickly, but I think you have the tools to be able to work this out on your own. Yeah.
Would you just use inverse trigonometric value to find inverse trigonometry to find the angle?
Yeah, that's exactly right. So let's suppose you wanted to find this angle right here. That is the angle that that vector makes with respect to the horizontal axis. Well, you know what the vertical part of it is. You know what the horizontal part of it is. So tangent of theta is opposite over adjacent. So the inverse or arctangent of the ratio gives you the angle itself, right? So theta then, maybe I'll call it different because I already called something else theta. Let's call it phi, is going to be the inverse tangent or arctangent of, so tangent is opposite, so it would be this right here, the vertical part, the F1y, over the horizontal part, which would be F1x plus F3, right? Does that make sense? So that way you can figure out what this angle phi is right there, right? So again, there's nothing, this problem isn't extraordinarily complicated, but it takes a lot of sustained thought and careful step work, right? So there's really, the concepts that go into this are fairly simple. Coulomb's law, and then some geometry and trigonometry. And we're using vectors to describe the components of these forces. All right, are we good? Okay, let me say, I know we're out of time. Let me say one other thing about the other homework problem. The other homework problem, let me just explain what I'm asking. You've got these two charges, and I don't remember what they are, what their values are, but I think one might be +2 and one might be -1. I don't remember what their charges are. But the question is being asked, if you were to take these two charges and like glue them down to the chalkboard, is there a place that you could put a third positive charge, let's say, so that there's no net force on it? And if so, where? So let's suppose you were to put it like right in the middle. If you were to put a positive test charge plus Q in the middle, what do you think would happen to that? Would it be pushed one way or the other? It would be pushed to the left, right? Correct? Because this one is repelling it to the left and this one's attracting to the left. So those two forces are going to add together to give it a force to the left. And what if you put it kind of here? Well, the same thing's going to happen. Anywhere in here, it's going to feel a force pushing to the left. Is there anywhere in this plane that I could put this charge so that the sum of the forces acting on it balance each other out exactly? And if so, where would that point be? Okay, that's the question I'm asking. All right. So think about, again, before you start plugging in numbers, think about like what might happen in different regions. And then from there, and I don't know if I got the numbers right, I'll look at the problem. But then start figuring out how to mathematically represent what you're trying to get at. Okay? All right. See you tomorrow.